Let's try this polynomial approximation for log of x, because people like log even less than cosine, right? So it'd be handy to have a polynomial approximation for it. Let's focus near x equals 1, because if we tried it at x equals 0, well, log of 0 is undefined. It's kind of negative infinity. It seems like we shouldn't have that in our polynomials, right? So let's focus somewhere nicer. It'll take some extra thinking in just a minute to handle this new idea of not focusing at x equals 0. So we'll have to think about that when we get to it. So let's make the same table as before. At order 0, we just have f, which is log x. F prime, what's the derivative of log x? It's 1 over x, which we could write as x to the negative 1. What's the second derivative? What's the derivative of x to the negative 1? It's negative 1 x to the negative 2. What's the third derivative? It would be that negative 1 times that negative 2 times x to the negative 3. And then the fourth derivative would be the negative 1 times the negative 2 times the negative 3 times x to the negative 4. I think we've got the pattern here. We don't need to go any farther. Then we should find what's the derivative value, and what do we want to plug in for x? Well, remember we said let's focus near x equals 1. So we'll use that here. You could do it at 2 or a half or a tenth or a 5 trillion or whatever, but for pedagogical reasons, let's stick with 1. So what do we get here? What's log of 1? That's 0. What's 1 to the negative 1? That's just 1. Negative 1 times 1 to the negative 2. Well, 1 to the negative 2 is still 1, so we get negative 1 there. Negative 1 times negative 2 times 1 to the negative 3. We just get negative 1 times negative 2 times 1, you could say. And negative 1 times negative 2 times negative 3 times 1. And then how about the polynomial terms? Well, it seems fairly straightforward that we should just copy this. That never had an x or a t on it anyway. But here, we should take the 1, and that's the slope. It's kind of the slope right now, where now is time 1, or x equals 1. And what have we done before about dealing with a slope and a linear term, right? This is the first derivative, so we should have a linear term. Well, let's remember the tangent line formula. Which is L of x equals f of c plus f prime of c times x minus c. So that said, you have your constant term, which is like our 0, and then a slope times how far away from your anchor point you are. C is kind of like the central point or anchor point. And here we want to say, take the slope and multiply by how far away from our anchor point we are. So we'll write here times x minus c. That's actually c is 1 here. So x minus 1. And then similarly here, we'll copy this coefficient and we'll say how far away are we from our anchor point. That would be x minus 1. And then square that and then divide by 2 factorial. Same system as before. And then our coefficient here is what? Positive 2 times x minus 1 cubed divided by 3 factorial. And then here we've got a negative 6 times x minus 1 to the 4th over 4 factorial. So if you add those all up, that's our polynomial approximation. So maybe we should go check that. All right, so we've got log shown here in red, and then we'll show the 0th order approximation at x equals 1. And that seems kind of silly, but you know, right there, it's pretty good, predicting pretty good values of log y. Then let's do this first order approximation in orange. That seems pretty good. That's our tangent line. And then our second order approximation does seem to be staying closer to the red curve here than the orange curve is, and closer here than the orange curve is. And then we'll throw in our third order approximation, our cubic, and again that seems to be staying closer to the original red function than even the parabola is. And then our fourth order, so that does seem to be staying pretty good there. Now it does seem to be diving pretty quickly over here, and we'll come back to that in a few more videos, but it does seem like it's doing a good job kind of in this region at least. So just to wrap up here, Taylor polynomials will say that they focus at a horizontal position of C. Up here we're using kind of C equals 1. That was kind of our anchor point, same way we do for tangent line formulas. And in the polynomial terms, we write x minus c to the n over n factorial. A lot of the examples we tried earlier were focused at time 0, and so that has its own name. That's called the Maclaurin Polynomial. So it's the same basic idea as a Taylor polynomial, but it always is focused at c equals 0. And then you can just say, well, if x minus c is x minus 0, I don't even need to write the subtraction. I can just write x to the n divided by n factorial, of course. So Maclaurin polynomials are just a little bit simpler than Taylor polynomials, and they're good when you don't mind focusing at a horizontal position of 0.